Good morning, everyone. So let's get the lecture started. Any questions that you guys might have?
You said that we have to remove that one empty piece from the div, and I tried it. And in that piece, since I tried to evolve the scalar coupling and carbon chemical separate, but after evolution, I wasn't able to solve it completely.
I see.
I got both the terms, but I wasn't able to solve.
Okay. Why weren't you able to solve? Were there too many terms?
Yes, I got 4 terms. I tried to write that COSY, COSB, and sin A, sin B.
Yeah. Right. So this is what you're trying to do. Is that right?
Yes.
Would you agree here you would have something like 2H, HX, something like HX, CZ. And then here you would have something like 2HZ, let's say CY, right? In this T1 duration, you have 2 terms, the carbon chemical shift and the scalar coupling, right? So when you let it evolve, since these 2 operators commute with one another, you can operate one first and the other second. So I would prefer to do the chemical shift first. So 2HZCY on T1 of omega CCZ will give 2HZCY cos omega CCZ minus 2HZCX sin omega CCZ. Right? Now, when I have both of them and I'm trying to evolve it with T1 and pi j HC to CZ, HZCZ, what you're going to get is cos omega CCZ. Yes.
Cos omega CT.
That's correct. I'm sorry. It should be cos omega. Thanks for finding it out. Yeah. Okay, to HZ CY cos pi j T1 minus HX sin pi j T1, right? Then minus sin omega C T1 to HX HZ CX cos pi j T1 plus HY sin pi j T1, right? Now, how many terms you got? You got cos omega C T1 cos pi j T1 to HZCY minus cos omega C T1 sin pi j T1 HX, right? Minus sin omega C T1 cos pi j T1 to HZ CX. Then finally a minus sin omega C T1 sin pi j T1 and then HY, right? The only last part that is left out is tau 180 tau with simultaneous 180 and INS, right? This is only going to evolve pi j to HZCZ term, right? Right? So therefore, the only 2 terms that you can actually reduce this down to are these 2 terms.
So what I did was that I tried to use that sin A minus B or cos sin B minus B.
You don't have to do that right now.
So I got it.
You got the idea. So that's why some of the times you don't have to do everything to get your answer. Sometimes you can cut short your steps and you already know this is the one we chose last time.
Yes.
Right? Because of the phase that we set up, you can always choose this also. The only negative thing here is that it's a sign modulation, in which case the next experiment, you can get the cos modulation. You can choose, this will, okay, the C, after you change this, remember, you can change the HZ to X or Y. With the, oh, I forgot the 90-degree pulse. That is a 90-degree pulse. Okay, actually, let's do that 90-degree pulse. which phase? Shall we keep it X phase? So 90X on both, let's assume. So it will become 2HY with a negative sign. CY also, if you apply a this pulse, it will become plus CZ, right? This is one term. HX will remain HX. And HZ CX will become HY CX. Correct? Multiple quantum term. HY will become HZ. After the 90 pulse.
Yes.
No more pulses are left. They'll change the order of coherence. MQC won't be observable. Polarization not observable. Now you have only two terms that are present. And what is going to happen? You have a tau 180 tau, where only 2CZHZ, the scalar coupling term, will evolve. In which case, this will nicely refocus to CHX, while this will become antiphase to 2HYCZ. Isn't it? When you let for allow for evolution, you realize that this becomes an antiphase term, while on the other hand, you have a nice in-phase term that you could use, the decoupling. So overall, what you're able to see, the only addition that comes up to this entire scheme of things, when you remove the 180-degree pulse at the middle of T1 evolution from the proton channel, instead of having cos omega c T1 HX, you will end up getting cos omega c T1 cos pi j T1 HX. You will always do quadrature for this by repeating the experiment by changing the phase of the first 90 pulse in the carbon channel. Therefore, you will get the sine omega c T1. You do repeat the whole thing, you will still have only cos there. Okay. Therefore, this part will give you exp I omega h T2. That's what is following. This part together with quadrature detection will give you exp I omega c T1. The part that's going to remain is cos pi pt1, right? So therefore, you can still simplify this such that it's exp by, I pi j T1 plus exp minus I pi j T1. That is the scalar coupling. Exp I omega c T1, exp I omega h T2. Right? Slowly, what you're able to understand is that you can incorporate both put together here. Right? This is an entire multiplication that's being present. And all these are the T1 index only, not the T2 index. Therefore, overall, what would you end up getting? 1/2 of exp I omega c plus pi j T1 plus exp minus, plus I omega c minus pi j T1 multiplied by exp I omega h T2. So this is a T1 term. This is only based on T1. This is only based on T2. So what is happening is that instead of getting one chemical shift, here you would have gotten only one chemical shift correlated with each other. On the other hand, what you end up getting here, you get up omega c plus pi j convoluted with omega h plus omega c minus pi j convoluted with omega h. Of course, there is a half term for both. So therefore, the signal intensity does reduce, but the scalar coupling of protons still evolves. So if you might imagine the carbon-proton experiment, which gave you chemical shifts at omega h and omega c previously. So let's say that one was a peak right here. In this experiment, it's only going to be split by the 2 pi j hc. Did that make sense?
Yes.
That's the only difference. Okay. Now, instead of doing all this, you keep the same HSQC. You literally keep the same HSQC pulse program. In the T2 evolution time, do not decouple. Currently, we did an experiment not decoupling in the indirect dimension, which is the carbon dimension. Could do the same equivalent, but not decoupling in the direct dimension. In such a case, what you're going to end up getting. So this is 180 pulse at T1 by 2 is absent. This one, decoupling during T2 is absent. So in theory, you can measure the one bond proton carbon coupling either from the F2 or from the F1. F1 is the indirect dimension. F2 is the direct dimension. The second part makes sense to you? Yesterday, we said we have the decoupling here. Therefore, we have the decoupling here. Therefore, the only term that's going to evolve is carbon chemical shift. We said just because decoupling is there, 2Hz term will not evolve. Just because this is there, 2Hz term will not evolve. That is decoupling. Now, let's say I turn this off. What do I mean by turn it off? I just don't apply this. All this is within my reach, isn't it? Let's say I don't apply this, then what happens is my next question. In such a case, you're going to get a spectrum where the J coupling does not come in the indirect dimension. It does not come here, but it ends up coming here because it will be T2 modulated. Is that true? Right? So one can actually measure the one bond J couplings in the direct or the indirect dimension. Now, let's take it to another extreme condition where you did not decouple in the T1 or during T2 time periods. What do you expect to get in such a point? You are expected to get a spectrum that looks like this. So every CH potentially gives 4 resonances. Since we end up decoupling in carbon and decoupling in proton, you get a single one. The HSQC that you see is decoupled both in the proton dimension and the indirect carbon dimension or nitrogen dimension. Okay, slowly I'm making you understand how the density matrix formalism will help you understand the outcome of an experiment when you change something. Yeah, did that answer your question? Yeah, good. So I asked one more question. My question also was, in the HSQC pulse program, the end of the inf, we have the Y phase. Don't change it to Y, keep it at X. Did any of you solve that example? But essentially, if you do not change the phase of the inf pulse, you'll still remain in the MQC.
Yes.
Right? So that's the only outcome. So definitely try doing this. This might be a question I'll end up asking. Okay? Okay. So let's take a few other examples. Any doubts in the data that I showed yesterday? You guys want me to show it again, or we are okay without it? Okay, so let's move forward. Let's see other 2D NMR experiments. So let's try to focus a little bit on proton-proton correlation experiments. Until now, we saw carbon proton and nitrogen proton. Those are called heteronuclear correlation experiments. These are called homonuclear correlation experiments. All right. So one of the simplest examples that I could take here would be the two-dimensional J-resolved experiment. And this is the T2. Okay. I'll give you guys 2 minutes to solve it, or maybe 5 minutes to solve it. Can you guys start? So what we are trying to look at is an IS spin system. Both are protons. So the pulses are active on both I and S spin system. And start with IZ and walk through what happens throughout the pulse program. Okay, let's get started. I want some of the students to start speaking. Abhay, how would you proceed?
So first, with the 90-degree expulse, it will go to -5, right?
Correct. That was easy. Then what happens?
And, it's tau 180 tau.
Therefore,
chemical shift won't evolve and scalar coupling will.
You said chemical shift will not evolve, correct?
It will refocus, sir. Yes.
Yeah, so no evolution. The only term that might evolve is the weak coupling term.
Yes.
You think it will evolve or not?
It will evolve.
Good. So how do you think it's going to evolve itself?
Sir, Iy cos pi j t1
Good.
minus 2ix sz sin pi j t1.
Right? Now, during T2, what all will evolve? The chemical shift will evolve. So would the scalar coupling again. Is that right?
Yes, sir.
So we can actually take one of these terms. So maybe we can take the ix cos pi j term and then let it evolve. Okay, so let's say cos pi j t1. Let me first evaluate to the chemical shift. Cos omega I t2 minus ix sine omega I t2. Right? Is that right, Abhay?
Yes, sir.
And then sine pi j t1. So let's take the next term, 2ix z cos omega I t2 plus iy sine omega I t2. Okay, so that's where we are. And then the next thing that we have to do here is to evaluate with respect to the scalar coupling. So let's evaluate with respect to the scalar coupling. This is not required. Pretty sure you guys already know if you evaluate the chemical shift and scalar coupling, a doublet ends up coming, but let's do it just for the sake of completeness so that you guys understand how does this pulse program work. So cos pi j t1 cos omega I t2 iy cos pi j t2 minus 2 ix se sine pi j t2. Right? You also would have the x term. The x term will be something like cos pi j t1 sine omega I t2 and then ix cos pi j t2 plus 2 iy z sine pi j t2. Right? Yeah, I think I made a small mistake here. This one would be plus 2 IYSZ. Correct? Everybody still following? Then let's see what other terms we got. Minus sine pi j t1 cos omega I t2 2 IXSZ cos pi j t2 plus IY sine pi j t2. Then finally, what do we got? IYSZ. And is that a minus? Yes. Minus sine pi j t1 sine omega I t2 to iy z cos pi j t2 minus ix sine pi j t2. These are the terms that we got. Yes. The reason why I evolved everything is that let's say we keep our acquisition along y-axis. So therefore, I'm only going to focus on these two terms. And what are those terms? Cos pi j t1 cos omega I t2 cos pi j t2. And then you also have minus sine pi j t1 cos omega I t2 and then sine pi j t2. Right? So this is what we have gotten. And what you're, and these both are the IY terms. The basic thing that happens here is that, remember cos and cos sine, how are they going to give you signals? Cos is going to give you an in-phase doublet. A cos sine is going to give you an anti-phase doublet. Is that right? So what is going to end up happening here is that they will destructively interfere. What do I mean by this? So cos omega I t2 cos pi j t2. These are the two you got. So this is going to give you let's take the other one also. So that's going to give you an in-phase doublet. Whatever I'm saying also has a quadrature component that comes into it, where the next scan will have the I part of it. Okay, so this one is going to give you the reverse of it. Okay, both will have the same 2 pi j coupling. You're going to get only one of them. And if you do the quadrature, you'll only get the other of them. Okay, so let's keep it at this point right now and ask what is happening in the T1 dimension. Remember, you will repeat the experiment by changing the phase of this pulse again to get quadrature detection. You could do that where you will get cos pi j t1 plus I sin pi j t1 to get phase sensitive. But many times people don't do that. They just do it a single scan experiment because we are only able to see, we are measuring scalar coupling from the indirect dimension. So what is going to happen? It's going to split into a doublet in the indirect dimension. And you have this kind of a phase relationship in the direct dimension. The spectrum is going to look like this. So let's say this is the proton on both axes, right? But if you're able to see in the T1 axis, you're only going to see based on J coupling differences because there is no chemical shift evolution that happens here, right? You do not get chemical shift evolution from here. You only get scalar coupling evolution. So let's say this is the zero of scalar coupling. That is, there is no scalar coupling. When do you have no scalar coupling? When it's a singlet. When you have such a situation, you get the signal similar to what you would have gotten otherwise. Meaning that you will get a peak only at omega I, and that's about it. On the other hand, if you have a doublet which splits the signal, you will interestingly get the signal of this kind. Because of the destructive interference I'm talking about, you won't get these two signals. You will just get them such that the difference between these two peaks will be the 2 pi j coupling that is being present. You might ask, why are we trying to do a complicated experiment like this? This would have otherwise come as a doublet in the direct dimension. When you're working with biomolecules, for instance, metabolic fluids, which have a lot of small molecules that are being present, to get them from the direct 1D experiment is tough. Even for camphor, we saw that is the example. So at that point, you do this experiment called two-dimensional J-resolved experiment. This is called the 2D J-resolved experiment, J-res experiment, where in the indirect dimension, you get the scalar coupling, and from the direct dimension, you get the chemical shift. So this way, one could reliably measure scalar coupling from the indirect dimension. They do one more aspect here. What is that aspect? Let me try to show it to you quickly. So one more aspect that they do is to tilt the spectrum. Once you tilt the spectrum, how do you tilt it? You tilt it along that axis, meaning that you tilt it above this such that this gets aligned, and therefore you will get a 2D that looks like this. You'll get a 2D instead of having peaks of this kind. You'll actually get the peaks tilted, which nicely match this way. So this way, the measurement of J coupling becomes easier. You improve resolution across the entire spectrum. This is for a simple doublet. For a triplet, you would have gotten something of this sort, where this matches with omega I, where this is the zero of scalar coupling. So if you measure this difference, will give you the scalar coupling. So if you end up tilting it and getting the spectrum, you will get a nice triplet along the indirect dimension, which will help you measure the scalar couplings. So what we are able to see here is that as we start to play with the pulse program, you can extract any type of information that you prefer to get. This is one example of, we did measure the scalar coupling of the methyl group in ethanol, which comes up to be 7 Hertz between the methyl proton and the methylene proton, right? But not always it's very easy to measure these from proton 1D because there'll be a lot of crowding. And in this way, what you are also able to see is that if you take a projection after tilting the spectrum, whatever came up as a doublet, so this experiment in a proton 1D would have come up as a triplet, right? But after tilting in the 2D J-res, if you take the one-dimensional spectrum, you actually get a proton decoupled one-dimensional NMR spectrum. We saw carbon spectrum decoupled with proton. You guys remember, all came as singlets. True? Now, if you do the 2D J-resolved experiment, get the 2D, tilt it and take a projection. What is a projection? Just sum up from the top. What will be the shadow if you blow torch from here? Then all of these will line up at the chemical shift. So this way, what is going to happen in ethanol spectrum, although you're expected to get a quartet and a triplet, after you do the 2D J-res and you take a projection along F2, what you're going to get is a single peak. So this way, what has happened? Oh yeah, you're able to improve the resolution of the proton spectrum by getting 2D and taking a projection. Alternatively, the 2D experiment also gives you very reliable ways of measuring scalar coupling.
The spectra part which you explained from the time evolution part.
This one.
Yeah, this one.
Yeah. What I will do is to go and write it out explicitly and send it to you, but we can prefer to take a look at only this part. Okay? Just for the sake of simplicity. What you're able to see is that this part indicates you're going to split into an in-phase doublet. True?
Yes, sir.
Okay. Do you understand that this will split into an anti-phase doublet?
Yes, sir.
So taking a combination of this, you will not get 4 peaks. You will only get the 2 peaks, this and not this and this. Right. So that comes up due to the combination of this, and then you have a cosine modulation, which will split it. So therefore, you will get only these 2 peaks. And these are not very convenient to analyze, because if you have too many resonances close by, you will have many peaks that are close to each other. So basically what generally people end up doing is rotating it by, I think, 45 degrees in order to get something like this. And therefore, all the indirect dimension information that's being present will be the scalar coupling.
Yes, sir.
Did that make sense?
Yes, sir.
Then I took one additional step. I said, take a projection along this. Previously, if you took a projection along this, you would have gotten the doublet as much as you gotten in the 1D experiment, correct? But here, if you take the projection, you will actually get only a single line. This means that you effectively decoupled protons from protons without applying any pulses, special pulses. Right? So getting a proton decoupled proton NMR spectrum is not easy. Why? Because you cannot decouple the channel that you are acquiring. Decoupling meaning applying pulses, 180-degree pulses. When you're applying pulses, you cannot receive signal because that will cause a problem. There have been other ways that people have come up where they end up applying 180-degree pulse between the dwell time. If your dwell time is 50 microseconds, you can apply a 20 microsecond 180 pulse to refocus, right? But that causes other complications. You have to selectively refocus and all that. But what you are seeing here is that just by doing a 2D jail-resolved experiment and taking a projection gives you a proton spectrum that's proton decoupled. So instead of seeing complicated spectrum, for instance, as we saw in camphor, you'll actually get all singlets in the proton. Would you agree with that? That will make your spectrum analysis easy, right? Then you'll say this is not an important application for camphor, but it's an important application for something like biofluids, where people take a blood to analyze with NMR, which has too many things in it. At that point, you want a simple proton NMR spectrum to analyze what's going on, what metabolites are there. You only want chemical shift to start with. So you run a regular proton 1D and maybe you'll run a 2D J-res, tilt it and get the proton decoupled proton 1D. So let me go to the next experiment. That is one of the hallmark experiments, the first 2D experiment that was proposed in 1970s and implemented in late 1970s, mid to late 1970s. So what the experiment is called a COSY experiment, correlation spectroscopy. We are only talking about homonuclear experiments right now. So this will be called as the proton-proton COSY experiment. Yet again, you have to imagine yourself to take I and S spin system. And we can start with the I spin system at equilibrium. Okay. And then we can start with the 90x pulse, which is going to take it to minus IY. We can still assume a weak coupling approximation so that chemical shift evolution and scalar coupling evolution can be done in any order. Okay. So now let's do the T1 evolution with chemical shift. What are you going to get? You're going to get minus IY cos omega I T1 plus Ix sin omega I T1. And then as you continue T1 pi j 2 IZ SZ, you will have something like minus cos omega I T1 Iy cos pi j T1 minus 2 Ix SZ sin pi j T1 plus sin omega I T1 Ix cos pi j T1 plus 2 Iy SZ sin pi j T1. Okay. Then what we have to do is to do a 90-degree pulse. And I've taken along the x-axis. Okay. So what is going to happen? Let me just copy this and write it so that it's easier for me. Remember, these are all hard pulses. These are all hard pulses. So therefore, it will affect I and S. If you apply X phase pulse, the Y becomes plus Z. So this goes to plus Z. So let me just change the color so that it's a little more easier to follow. It goes to Z, right? Then if you have along X, X remains X, Z becomes minus Y, right? So minus of minus will become plus here, Ix Sy with a minus sign. Doesn't matter, it's multiple quantum. If you have X, X along X will be in phase, right? Okay. Then you have another 90-degree X phase pulse. What is that going to make it? That's going to change this to Iz. Sz will become Sy with a negative sign, isn't it? Right? And what we are able to see here, these two terms, we don't have to worry about. Because it's polarization, there are no more pulses, only T2 delay is left. We will not see this. True? Similarly, this is multiple quantum term. We will not see this. The single quantum terms that are in our hand are these two. Of course, this is antiphase single quantum term. Let's see what happens to it in T2 evolution. So I'm only going to take this part of it and go forward. The COSY experiment. 2 IZSY. This is what you had, right? Now T2 evolution on omega I Iz, and now I have to also invoke omega S SZ because the S component is there. Of course, you can repeat the entire exercise starting from SZ, where you'll just do the opposite set of discussion, nothing else. It's one and the same. So here, what are you going to have? You're going to have sine omega I T1 cos pi j T1. Immediately, you're able to see that this is going to give you an interesting combination of an antiphase doublet in the indirect dimension. Anyway, we'll wait for that in a moment. Ix cos omega I T2 minus Iy sin omega I T2. And then minus sin omega I T1 sin pi j T1 2 IZSY cos omega S T2, right? Minus Sx sin omega S T2.
Ix omega I T2.
Ix omega I T2. Ix omega I T2. What's that? So I started with Ix and I'm evolving only with this. This will not evolve because that will commute. So I'm evolving this with this, while this with this, because this will commute with this part.
So this will be plus I1.
That's correct. Thank you very much. Thank you very much. Appreciate it. Okay. All right. Now let's still go further. And what do we want to do is, so a lot of terms are coming up, and it's going to be evolved with pi j 2 iz as z term now. So let's write this. Sine omega I t1 cos pi j t1 cos omega I t2 ix cos pi j t2 plus 2 iy as z sine pi j t2. Okay, so the next one is going to be sine omega I t1 cos pi j t1 sine omega I t2 iy cos pi j t2 minus 2 ix as z sine pi j t2. Okay, please look out for mistakes that I might do. I'm talking and writing, so it might be inadvertent. I request you guys to pay close attention. 2 iz sy cos pi j t2 minus sx sine pi j t2. Now the last term would be plus sine, is that plus? No, minus of minus should become plus, right? Maybe I did a mistake somewhere. It has to be kind of symmetric. Anyway, we'll see. Sine omega I t1 sine pi j t1 sine omega s t2 sx cos pi j t2 minus sy sine pi j t2. Too many terms, right? Sorry, made a small addition. One more term will be there. Minus 2 iz sy. Okay? Because sx will become iz sy. Which one? It should be plus. It should be plus, yes. Plus 2 iz sy. That's correct. We have many terms. Let's see what are all the terms that we got. We have an ix term and we have an sx term. Right? We have iysz, izsy. Thankfully, this will go away because they are not detectable. If you take an I plus S plus operator, this will go away because the trace with respect to I plus S plus will be 0. Correct? Because I plus has ix plus iiy. Whatever you do the multiplication will be a traceless matrix. So therefore, we can conveniently forget about this one, forget about this one, forget about this one, forget about this one. Yeah? The ones, there is a mistake that we have done. You can't have two ix terms. One of them should be iy. Did I do the 90 pulse correct? 90x will make z correct. This is correct. 90x will keep this and switch this. This is correct, so we can neglect this. X on x will remain. X on y will make it z. Yeah, this is also correct. Minus 2 izsy, minus 2 izsy. Ix will go iy with chemical shift. 2 izsy. That is a mistake we did. See, I'm telling you, there was a mistake. They should have been minus 2 izsx. Okay, so that was a mistake. Right? So it's luckily not a big mistake, only the penultimate step we did. So let me erase this and rewrite. That's the only term I need to rewrite. I'm also giving you guys an idea how to write your exam. The moment you are able to figure out there are asymmetric terms, I was looking at symmetric terms. On the other hand, I got sx and sx. That cannot happen. When you have ix and iy, you should have sx and sy or sx and sy. You'll see it in a moment. And I realized there's something wrong. So I'm proof correcting myself. right? And these things happen. This is on top of the two mistakes that you were able to point out as I was writing. So these things happen even for people who practice a lot. So go practice a lot in this week. That's the main purpose why I'm finishing up 2D as much before we go for the break in Bhopal. Okay, so this is going to be minus will be plus 2Iz cos pi j t2 plus Sy sin pi j t2. Now life is okay. You have an x component, y component, you have an x component, y component, and plus x plus y plus x plus y. So things are okay. They're quite symmetric. Can we take the acquisition also on the x phase, which means that the observable A operator is Ix plus Sx, not Ix Sx, Ix plus Sx. Okay, therefore, what is going to happen? This will not be observable. Similarly, this will not be observable. Your observables are one term here and the other term here. Everybody followed? What am I doing? I'm taking Ix, making a product. Ix square will have a non-zero trace. Ix Iy will result in Iz, which has a zero trace. So therefore, we will not be able to see this. Already, we have canceled the other terms due to other factors. Now, the only two other terms that are left are here. Sx with Ix will be 0. Sy with Ix will be 0. So Ix will only work with this. True? Similarly, if I take Sx, this will be 0, this will be 0, this will be non-zero, this will also be 0. So the only two terms that we have to worry about are these two terms. Do you guys agree with that? So what am I trying to say? The trace of my final density matrix with Ix plus Sx being the observable operator is only going to give me is equal to sine omega I t1 cos pi j t1 cos omega I t2 cos pi j t2. Then the other term that you have here, sine omega I t1 sine pi j t1 sine omega s t2 sine pi j t2.
Sine.
Sorry, this one. No, this will be sine, right?
Yes.
Maybe I did a mistake somewhere. Yeah. Yeah, these both share the sign. All the other three are, yeah, this is fine. Okay. I think this is fine. Check after you go back. So what do we learn from this? Okay, we got something complicated. How do we understand what it is telling us? That's the final spectrum that we need to understand. Take a look at the T1 and the T2 indices that are being present. In the T1 index, you have a sine omega I with a cos pi j T1. Right? So one can always write this as sine of omega I minus pi j times T1 minus sine, sorry, what is this? So this is sine A cos B, which is sine of A plus B plus sine of A minus B. Evenly. Sine of A minus B. I'll end up uploading this. Please follow it up what's been done. Okay. So go back, solve this. You'll get sine of A plus B plus sine of A minus B equivalent. If you take a look at this, this is cos. This is cos of A minus B plus cos of A plus B. But this is in T2 dimension. Most importantly, in both the T2 and T1, this term has frequency labeling with respect to only the I spin. What do you mean by that? You're going to fish out the chemical shift in F1 of I, and you're going to fish out the same chemical shift of I in T2 also, in F2 also. Okay, so this is going to be a cross peak, similar to the correlated peak that you saw. This is going to be a cross peak upon omega I in F1, omega I in F2. Similarly, if you pay close attention to this is a very interesting term. It has labeling of omega I in T1 and omega S in T2. So this is going to be omega I in F1 again, similar to what you saw here, but in the T2, it's omega S that's going to get frequency labeled. Similarly, instead of doing this entire formalism starting from IZ, you can repeat this formalism starting with SZ. Don't do it, but it's very simple. Switch the indices of I to S and S to I. That's it, you're done. You don't have to do this. What I'm trying to impress upon you is that similar to the aspect that when you started from IZ, you got one omega I F1, omega I F2, and you get another one, which is omega I F1, omega I F1, and then omega S F2. So if you repeat the task with SZ, you'll get omega S F1, omega S F2, omega S F1, omega I F2. Just repeat it. Just the indices will be flipped. So wherever you have the same index coming in both F1 and F2, this is called a diagonal peak. On the other hand, wherever you have different indices being correlated, this is called a cross peak. What do we mean by this? Similar to the 2D correlations we have been seeing, let's say this is omega I, this is omega S, this is omega I, and this is omega S. We are talking about F1 dimension here and F2 dimension here in frequency. What you are able to see is that the diagonal peak correlates omega I comma omega I. So anything that comes up as omega I comma omega I and omega S comma omega S comes as a diagonal peak. On the other hand, you also have cross peaks that correlates omega I to omega S. So this one is omega I in F1 dimension and omega S in the F2 dimension, which is what you saw here. On the other hand, this one is omega S in F1 and omega 2 in F2. So therefore, that's going to be a cross peak here. So these are called cross peaks, while the red ones are called diagonal peaks. What have we achieved from this experiment? This experiment achieves the fact if two protons are scalarly coupled, then you'll get a cross peak, else you will not get a cross peak. Okay, so for instance, something like an ethanol spectrum, if you want to take it, this will be the diagonal peak. Ethanol had 3 peaks, which is the methyl, methylene, hydroxyl, methyl, methylene, hydroxyl, and the cross peaks would feature here, where we are able to see the methylene will talk to the hydroxyl and to the methyl, while the methyl to hydroxyl will not give cross peaks because the scalar coupling is small or not observed. Okay, that's the advantage of a COSY. What I request you guys to do for the next 1 week, it's a break at ISO Bhopal. Pune guys will also get 1 lecture, but please work on understanding HMQC. Go back, do it and see whether you understand HSQC. Also think about the passive coupling in both of these experiments. And understand how F1, F2 decoupling, if does not happen, what happens. I'm sorry, I'll finish in just like 30 seconds. And also understand how a COSY and 2D J-res work. Thank you very much.